Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss a new classifier, that is naive-Bayes classifier. Naive-Bayes classifier is a generative counterpart of logistic regression. It uses Bayes' theorem for calculating probability of a sample belonging to a class. It makes strong, which is rather naive, conditional independence assumption between features given a label. It is simple yet very powerful classifier that is used extensively in applications like document classification and spam filtering. Since naive-Bayes classifier is a machine learning algorithm, it has got 5 different components. So let's look at these components one by one. The first component is the training data. So there are two types of naive-Bayes classifier, one for binary classification and second is for multi-class classification. So we have training data, which is D, which is ordered pair of feature matrix and labels. In case of binary classification, we have a label vector, whereas in multi-class classification, we have a label matrix. So we have feature matrix in both the types. Then we have a label vector in binary classification, whereas we have a label matrix in case of multi-class classification. This I that you see here is index of example. So this is an individual example. This is a feature vector corresponding to ith example, and this is label corresponding to ith example. Same thing goes over here, but here instead of a single value, we have a vector of values in labels for every example. So the shape of feature matrix is n comma m, where n is the number of examples and m is number of features. Label vector has shape of n and label matrix has shape of n comma k, where k is number of classes. So here the label has got a single value which is from a discrete set. It could be 0, 1 or plus 1, minus 1. Here it is a vector of discrete values. Now you can see the difference. The first difference is in the label, and second difference is the way individual labels are present in the training set. So let's look at the second part, which is model. So naive-Bayes classifier makes a strong conditional independence assumption. So that assumption, what is that assumption? The features are conditionally independent given the label. So this particular assumption enables us to express joint probability of features given the label as product of probabilities of individual features given label. Let's look at it mathematically. So this is a joint probability of features given the label. So there are m features, x1, x2, all the way up to xm given y. And because we are making this strong conditional independence assumption, we can write this particular joint probability as product of individual conditional probabilities. So we can write this as probability of x1 given y into probability of x2 given y, all the way up to probability of xm given y. And we can write this compactly with a product. So we basically take a product of all m features. So here product of probability of xj given y, where j runs from 1 to m. So we'll be using this particular equation again and again in this particular slide. So make sure you have noticed it well and you understand it well before proceeding further. So naive-Bayes classifier predicts probability, that is p of y given x, of class label y given a feature vector x. So we are interested in predicting the probability of a class label given the feature vector, and for that we use Bayes' theorem. So p of y given x is p of x comma y. This is the joint probability of features and label divided by the probability of the feature vector. So this particular probability is called as posterior probability, Then we have class conditional density. This is called class conditional density, where we are interested in using the class conditional density of every feature given the label. Here we have written this as class conditional density of a feature vector, and the naive Bayes assumption will help us break this down into the product of individual features, or product of individual class conditional densities of features. And then we have class prior. This is the prior probability, and the denominator is called as evidence. Now what we'll do is we'll try to simplify this equation further, this particular Bayes rule. So we say that the posterior probability of a sample belonging to class YC is equal to the class conditional density of the feature vector given label YC into the prior probability of YC given divided by the evidence. Now we can rewrite this class conditional density of a feature vector given label YC as with this particular form. So we basically will open this up and write down all the individual features instead of a vector notation. So we'll make those changes over here and here, and we can now see that so we have basically opened up this particular term and a term in the denominator. So now what we can do is we can express the denominator as sum over all k labels. So we'll get the denominator exactly in the same form as the numerator. So what we will do is, what we have done is we have said that this particular, the probability of an example, so example will come from one of the k classes, and hence we write this as a sum over all k classes of the joint distribution between the features and the label. So now we can write the denominator by applying the chain rule. So here the chain rule will be applied like, so we express the joint probability of features and labels as the conditional probability of the feature vector given the label into probability of the label. So we simply replace the denominator with this particular term, and now we get numerator and denominator almost in the same form, except that the denominator has a summation over all k labels. Now what we'll do is we'll rewrite the numerator and denominator following the conditional independence assumption. So these terms, right, so the class conditional densities in numerator and denominator will be rewritten using the class conditional assumption. So we know that, so the joint probability of the features given the label is expressed as product of conditional probabilities of individual features. So you can see that what we have done is we have brought this prior probability ahead, and then we have written this as the product of conditional probabilities of individual features. So we made that change in both numerator and denominator, and now we can write it compactly with a product notation. And we are familiar with this product notation. We have seen this earlier in this presentation where we were writing down the conditional independence assumption. Let's look at the parameters of naive Bayes classifier. So we wrote the probability of a sample belonging to class YC adds a ratio of prior probability into the class conditional density or likelihood divided by the evidence. Now what is not known here? So we do not know the prior probabilities, and we also do not know the class conditional densities. So there are k prior probabilities that are not known in order to compute this quantity, as well as we do not know k cross m class conditional densities. So for every label or every class, we do not know m of these numbers, where m is number of features. So we do not know the class conditional densities of individual features given the label. And you can see that this yc, this particular term and this term over here are one of these terms that we have already accounted for. So this is one of the k prior probabilities, and these are m of k cross m class conditional densities. So we need to estimate these quantities from the training data. So these k prior probabilities are p of y1, p of y2 all the way up to p of yk, and class conditional densities for one of the labels are x1 given yr, y2 given yr, xm given yr. So these are m class conditional densities, and since there are k such classes, we have k cross m class conditional densities. Now number of parameters for each of these densities will vary, and it depends on what kind of distribution is relevant for each of these class conditional densities. So it really depends on how we model this class conditional densities, and based on that the number of parameters will vary, and we will see some of the examples of different possible models of these class conditional densities. So let's try to figure out what exactly naive-Bayes classifier does at a higher level. So let's say this is our data. So there are two classes, y equal to 1 and y equal to 2. Let's say there are two classes. One is, let's say, blue points and then red squares. So what we do is we first estimate. So there are two dimensions or two features, x1 and x2. So what we do is first we perform the class conditional density estimation of feature x1 given y equal to 1 and y equal to 2. There are two classes, hence there are two different distributions that we will learn. Then we'll do the same thing for the second dimension, and you can see that the shapes of these distributions are different, so we are free to choose whatever distributions that are relevant. Then what we do is we perform the product of these two class conditional densities. Let's say for class 1, these two densities will be will perform product of these two entities, and we get something, we get a resulting data distribution for label 1 something like this, and for label 2 which is something like this, and this is estimated by performing the multiplication of individual class conditional densities. Now let's try to let's spend some time on modeling class conditional densities. So depending on the nature of feature xi, the feature could be a binary feature, right? Where, for example, word is present or not, so it becomes a binary feature. Then it could be a categorical feature, which is generalization of a binary feature. Instead of just two values, there could be c such values that are possible. Then we might have multinomial feature where we have word counts as features with an additional constraint that the sum of all word counts is equal to length of the sequence that they represent. So this length of, it could be length of the document that that These features are representing jointly. Feature could also be a continuous feature. It could be a real number. For example, area of an apartment in square feet is an example of a continuous feature. Let's study how to model the class conditional density of individual features given a label. So we use probability distribution for this modeling, and it depends on the nature of the feature xj. So if the feature is a binary feature, then we model its class conditional density using Bernoulli distribution. And Bernoulli distribution has one parameter, which is mu jc, and j and c here are the indices of the feature and class label respectively. The generalization of Bernoulli is categorical distribution. So if we have a feature containing categorical values, we can use categorical distribution, which has got e plus 1 parameter, where e is the number of categories, and for every category there is a mu value for that category, for that particular feature and a class label. So there are e plus 1 values, e plus 1 parameters in categorical distribution. If the feature has continuous value, then we use Gaussian or normal distribution for modeling the class conditional density of that feature. The Gaussian distribution has two parameters, mean and standard deviation. And finally, if we have a feature vector which represent some kind of counts, and with an additional constraint that the sum of counts is equal to length of, let's say, a sequence that it represent, which is for example a document, then we use multinomial distribution to model such a feature vector. Multinomial distribution has got m plus 1 parameters, where L is the length of the sequence, and then for each feature, each of the m features, we have n different parameters, which are mean values of that particular feature for that particular class label. So we need to estimate parameters of relevant distributions, one for each feature and for each class label. So we use a W vector, and W be the set of all parameters. It contains priors as well as parameters of class conditional densities. And we need to learn these parameters from the training data. Let's look at some of these distributions one by one. So when xj is a binary feature, xj is jth feature. Whenever jth feature is a binary feature, we use Bernoulli distribution to model the class conditional density, that is P of xj given by C. So Bernoulli distribution is parameterized by mu jc, and so with this parameter, the class conditional density is calculated as follows. So the probability that the feature will take value 1 is mu jc, and the probability that the feature will take value 0 is 1 minus mu jc. And we can combine these two equations into a compact form as follows. So we can write the Bernoulli class conditional density of feature j given class label c, which is parameterized by mu jc, as mu jc raised to xj into 1 minus mu jc raised to 1 minus xj. And now you can see that we can verify that this compact form is equivalent to what we have written over here. So when xj is equal to 1, we will substitute 1 for in place of xj. We get mu jc here 1 in place of xj into 1 minus mu jc, 1 minus 1. So we have mu jc raised to 1 and 1 minus mu jc raised to 0, which is, so this part becomes 1, so we have mu jc, and which is what we have here, right? So whenever xj is equal to 1, we have mu jc. And whenever xj is equal to 0, we are getting we can substitute xj as 0 over here, and you can see that when we substitute 0 in place of xj, we have 1 minus mu jc, which is again which is identical to what we see here in the second equation. So this is particular form is a compact form, or is a compact way of writing these two equations together. When xj is a categorical feature, that is, it takes more than two discrete values, for example red, green, blue, or roll of a die, we use categorical distribution to model the class conditional density of the feature xj. So class conditional density is represented as P of, or the probability of xj given by C. So let V1 to V2 up to Ve be the set of E discrete values. For the discrete set V, the class conditional density of the feature xj given label by C is parameterized by the cardinality of this set V, that is the number of events in V or number of discrete values in V, and the probability of each event or each discrete value. So those probabilities are given by mu j1c, mu j2c, all the way up to mu jec. So these are indices. The first index is for the feature, the second index is for the index of the value in the discrete set V, and the third one is the index of the label. And the sum of all these probabilities is equal to 1. So for a specific value of these from this discrete set, so xj equal to vq, such that vq belongs to this discrete set, or vq is one of the values from the discrete set, the probability of xj equal to vq given by C with a particular parameterization is equal to mu jqc. So what we'll do is we will write down all these mu parameters as a vector mu jc. And now what we can do is we can write the class conditional density, or the categorical class conditional density, in a compact form as follows. So mu j1c raised to 1 of xj equal to v1, mu j2c 1 of xj equal to v2, all the way up to mu of jec of 1 of xj equal to ve. So now what you can see is that, so this one, like 1 of xj equal to v1, or 1 of xj equal to v2, or 1 of xj equal to ve. So we are raising the power of mu to these values. So what does that represent? So 1 of xj equal to vq, right? So this is equal to 1 if xj takes the value vq. If it doesn't, then this particular expression will result into value of 0. So we can see that this compact form is equivalent to the following expression. So whenever the value of xj is v1, so only this particular part will be 1, all other powers will be 0. So whenever we raise any mu to the power 0, we get value of 1. So we end up with mu j1c wherever xj takes value v1. In the same manner, when xj takes value v2, we end up with mu j2c, all the way up to when xj takes value ve, we end up with mu jec. So the total number of parameters for all k classes is equal to k into sum over the jth discrete set. So each feature will have its own discrete set, and each discrete set will have some cardinality. So we have to sum up all these cardinalities across some features and multiply that with the class count, which is k, and that becomes the total number of parameters that we need to learn if all m features are categorical. So if we have less than or equal less than m features, then this number will reduce accordingly. So whenever the feature vector is a count vector, that is each component xj is count of appearance in the object it represents, such that the sum of individual feature values is equal to the length of the object, we use multinomial distribution to model the feature vector given the class label. So this is the first time we are modeling the entire feature vector rather than modeling individual features. So multinomial distribution is used for modeling documents, and these documents are represented by word counts. So again, it is parameterized by length of the object and probabilities of features, mu1c all the way up to mu mc, and where c is the class, is the index in the class label. So probability of the feature vector x given yc such that the sum of individual feature values is equal to length of the object. So it is given as n factorial divided by factorial of values in individual features into the product of individual mu's for each of the m features. So it's a product of mu jc raised to xj. So total number of parameters here are k into m. There are m parameters to be learned for each class, each of the class. So there are k into m parameters for multinomial distribution if the feature vector is a count vector representing the length of the object. So when xj is a continuous feature, that is, it takes a real value, we use Gaussian or normal distribution to model the class conditional density. So Gaussian class conditional density is parameterized by mean and variance. So it can be calculated with the following formula: 1 over square root of 2 pi into mu jc exponential of or e raised to minus half times xj minus mu jc divided by sigma jc squared. So xj is the value of ith feature, mu jc is the mean of xj for class yc, and these are standard deviation of xj for class yc. So this is basically 1D Gaussian. It models class conditional density for a single feature. Alternatively, we can use multivariate Gaussian distribution to represent the class conditional density of the entire feature vector. But it will have parameters that will be mean vector and covariance matrix. So instead of just having a mean and standard deviation, now we have a mean vector and covariance matrix. So mean vector has m components, whereas covariance matrix has m cross m components. In naive Bayes setting, since the features are conditionally independent of one another, all entries of covariance matrix except diagonal are 0. The diagonal entries represent variance of that feature. So the probability of the feature vector given the class label parameterized by mu and standard mu and covariance matrix, mu vector and covariance matrix, is given as 1 over square root of 2 pi raised to m, the determinant of the covariance matrix, into e raised to minus half x minus mu transpose into inverse of covariance matrix into x minus mu. So this particular term in the exponential gives a distance, right? It gives a normalized distance between the feature vector and the mu, and this distance is kind of normalized by the covariance matrix. In 1D case also, this particular equation, it gives us a distance between the feature value and the mean, and here we are normalizing it by standard deviation. So once we learn parameters of different conditional densities, we use them to infer class labels for new examples. So we assign a class label yc to a new example x that maximizes the posterior probability. So the class label that maximizes the posterior probability will be assigned to the example. So let w be the set of all parameters, and we assign the label that maximizes the posterior probability. So we know the definition of posterior probability. It comes from the base formula, so we have simply written the base formula, which is product of the likelihood and prior. So this is a class conditional density into the class prior divided by the evidence. Now since this particular value or the denominator is independent of yc, we can ignore the denominator from this computation. But we have to be cautious. When we ignore this denominator, we do not really get the probability values, and in order to calculate the probability value, we also need to calculate, we cannot ignore the denominator, but for the inference task, for time being, we can ignore the denominator and find out the class label that maximizes the product of likelihood and the prior, and evidence is going to be constant for all the features whenever we are, for all the classes whenever we are doing this computation. So we simply perform the multiplication of class conditional densities and class priors, and we select the class label that maximizes this particular product. Now we can expand the class conditional density with naive Bayes assumption. So this equation involves multiplication of many small numbers. So we are multiplying the class conditional densities of individual features, and there are m such features. So when we perform m multiplication of these small numbers, and also the prior probability is also a small number, there is a risk of underflow in this calculation. So we perform this calculation in the log space. So we apply log, and when we apply log on the product, it becomes sum. So we have sum over m features. We basically sum up the log of individual conditional densities, and we add the log of the prior of the class. So now we assign y to the one that maximizes this particular sum in the log space. So this equation that we wrote in the previous slide is useful for assigning a class label. However, it does not return the probability of an example belonging to class yc. In case we want the probability, we should use the following equation and perform also the computation of the denominator term, and this computation is a bit expensive if there are many classes. This calculation should also be performed in log space. In the next video, we will look at the remaining components like loss, optimization procedure, and evaluation matrix of naive Bayes classifier.